Hi, in this second module on classification, we'll go in more details about neural networks. I'll start giving a general definition of neural network and focus on the multi-layer perceptron. I'll show how to choose the different parameters involved in the network building, such as hidden units, activation, and error functions. Artificial neural networks are actually inspired by the way biological nervous system works. An artificial neural network can be defined as a large number of highly interconnected simple processing elements called neurons working together to solve specific problems. Usually, a neural network is structured in an input layer of neuron, one or more hidden layers, and one output layer. Neurons belonging to adjacent layers are usually fully connected, and the different types of architectures are identified both by the different topologies adopted for the connections and by the choice of the error and activation functions that we'll see later. On this slide, the left picture represents a self-organizing map, with all the units on one layer, while on the right there is a multi-layer perceptron with one hidden layer with 5 hidden units, and of course an input layer and the output layer. Now, in this slide I listed some of the most used neural network models. In few words, in feed-forward networks, the connections between the units do not form a direct cycle, like in the first figure. In recurrent networks, like the one shown in the middle, they do. Self-organizing maps are typically considered similar to feed-forward, but in reality they are quite different, as we'll see when we talk about clustering. Stochastic neural networks are built by introducing random variations into the network, and one of the most used are the Boltzmann machine or the restricted Boltzmann machine that are shown on the right. Now, let's start with the basic computational element called node or unit. A unit receives inputs from other units or from an external source in the case of the input units. Each input has an associated weight W, which can be modified during the learning. Then the unit computes some function of the weighted sum of its inputs and gives it in output. The multilayer perceptron is one of the most used supervised models. It consists of multiple layers of computational units, usually interconnected in a feed-forward way. In a multilayer perceptron, each neuron in one layer has direct connections to all the neurons of the subsequent layer, so it's fully interconnected. Now, let's see how the network learns. It uses a backpropagation approach. Roughly speaking, the output of the network is compared with the targets, and the weights are adjusted in order to minimize the sum of the errors. We have said that the network has one input level, one output, and 0 or more hidden layers. Actually, choosing the number of hidden layers and of the hidden units is crucial. And unfortunately, there is no magic formula that we can use. This number depends on the number of inputs and outputs, number of training cases, the amount of noise in the targets, the complexity of the function to be learned, as we'll see in a moment, depends on the activation function, and so on. For example, if we have too few hidden units, they can lead to high training and generalization error due to underfitting and high statistical bias. While if we have too many hidden units, we can have a low training error but high generalization error because of the overfitting. In this slide, there are some possible decision boundaries which can be generated by network having a threshold activation function and different numbers of hidden layers. For example, A, the first one, is a simple perceptron with just one layer and can be used for linear classification. Two layers networks, like in B, can generate decision boundaries more complicated, surrounding a single convex region of the input space. Networks with 3 or more layers can generate arbitrary decision boundaries that may also be non-convex or disjoint, like in the figure. Now, let's talk about activation and error functions. Changing these functions change not only the results, but also how we can interpret the outputs. Activation functions are used by most units to transform their inputs and are also needed to introduce non-linearity in the model. Some of the most used are linear, logistic, softmax, and tanh. Usually for the output nodes, you can apply the same function as for the hidden if the outputs are bounded. Otherwise, you can just apply a linear activation function. In this slide, there are 2 examples of activation function, step function and sigmoid. Now, say we want to have a crispy classification for a 2-class problem. In this case, we may use a binary classifier with just a step activation function. And in a step function, the output is a certain value, say 1 if the input sum is above a certain threshold, and 0 if the input sum is below a certain threshold. Sigmoid functions have the property of being similar to step functions, but with the addition of a region of uncertainty. Now, it has also been shown that a 2-layers network with sigmoidal hidden units and linear outputs units can approximate a continuous function to arbitrary accuracy. Now, let's talk about error functions. Most methods for supervised learning require a measure of the discrepancy between the network output values and the targets. Now, 2 commonly used error functions are the sum of the squared errors and the cross entropy. For example, using a multilayer perceptron with a softmax activation function and cross entropy error allow to interpret the network outputs as the conditional probabilities P of class 1 given X and of class 2 given X, where X is the input vector. In this way, we have an actual probabilistic classification. In few words, if you want in output the probability for each object to belong to a given class and you are using a multilayer perceptron, you have to use a softmax activation function and a cross-entropy error. Now, early stopping is a form of regularization used to avoid overfitting. In few words, we stop the training process when the maximum number of training cycle is reached or when we start seeing an increase in the validation error. That's because typically the validation error will initially decrease as the model fits the data better and better, but then start rising when the model begins to overfit. So the idea is to stop the learning as soon as the minimum invalidation error is achieved. For example, in the figure, the blue line is the training error and decrease always, while the red line is the validation error that at some point reaches a minimum and starts rising. And with early stopping, we want to catch that minimum and stop the training there. Now, in this video, we have seen how to use a multilayer perceptron for classification. First, of course, we need to create a proper training, validation, and test sets, and choose the cross-validation approach we want to use. Then we need to choose the topology. For example, the number of hidden layers and the number of hidden nodes per layer. And we have said that there is that rule of thumbs don't work in this case, and they depend on many factors. Then we need to choose error and activation functions according to the results we want to have. For example, if you want to have a binary crispy classifier, we can use a step function and a sum of square errors, or if we want to have a probabilistic classification, we need to use a cross-entropy error and a softmax activation function. And then we need to choose also the activation functions for the output units, depending on if they are bounded or not. If they are bounded, we can use the same activation function of the hidden layers. If they are not bounded, we can just use a linear activation function. Then, once we have all the network, we can run the training process and assess the results using a test set. And when we are happy with the accuracy, the precision reached, we can freeze the network and use it on new data, so for the actual classification. Now, in the next lesson, we'll see other models and also some tools useful for classification.